Ever wonder how robots are built? The complex machines that are shaping our future? Robotics, a realm where science and imagination intertwine, is pivotal in today's rapidly evolving technological landscape. As we stand on the brink of a new era, understanding how these mechanical marvels are constructed is not just intriguing but essential. Robots, in essence, are intricate amalgamations of design, assembly, programming, and rigorous testing. These fascinating creations commence as mere blueprints in the minds of innovative engineers who then breathe life into their designs. The process might seem daunting, but it's a remarkable journey of transforming a simple idea into a tangible, functioning entity. From autonomous vehicles to surgical assistants, robots are progressively influencing diverse facets of our lives. The ability to create such machines, to envision and actualize ideas that can redefine the future, is truly a testament to human ingenuity. Dive into the fascinating process of building robots, a journey that starts with a simple idea. Building a robot starts with a detailed plan. This statement is as true as gravity. In the world of robotics, planning is the bedrock upon which everything else stands. It's the blueprint, the roadmap, the game plan, the strategy. What does this planning entail? Well, it involves outlining the robot's purpose, structure, and components. Why is the purpose important, you may ask? The purpose of a robot determines its design. A robot designed to navigate Mars' rocky terrain will drastically differ from one designed to assist in delicate heart surgery. The purpose shapes not just the physical design, but also the type of sensors, actuators, and even the programming language used. Next, we delve into the structure of the robot. The structure is the skeleton, the framework that holds everything together. It needs to be designed with precision and care. The structure should be sturdy enough to house all the components and withstand the environment it is designed for, yet flexible enough to allow for smooth movement and operation. The components are the heart and soul of a robot. These include motors, gears, sensors, power sources, and control systems. Each component has its own function and role in the robot's operation. For instance, sensors provide the robot with information about its environment, while motors and gears enable movement. The power source fuels the robot, and the control system is the robot's brain, interpreting sensor data and sending commands to the motors. At this stage, a symphony of collaboration unfolds among mechanical, electrical, and software engineers. The mechanical engineers focus on the physical aspects of the robot, while the electrical engineers work on the power, sensors, and control systems. Meanwhile, the software engineers start sketching out the code that will breathe life into the robot. It's a fascinating process, isn't it? The creation of a robot is a testament to human ingenuity, a perfect blend of art and science. And all of this starts with a detailed plan. With a solid plan, the next step is bringing the design to life. Scene script. Once the design is ready, the next stage is assembling the robot. Now, let's dive into the fascinating world of robotics assembly. The process of assembling a robot is much like piecing together a complex jigsaw puzzle where each component has a specific place and purpose. The choice of materials is crucial here. Depending on the function of our robot, we may select from a variety of materials such as metals, plastics, or even advanced composites. Durability, weight, and cost are all factors to consider when selecting materials. The mechanical assembly involves putting together the robot's structure. This could include creating the skeleton or chassis, as well as attaching motors for movement. Each part must be meticulously assembled to create a solid, functional unit. Next, we move on to the electronic assembly. This includes the robot's nervous system, consisting of wires, circuits, and power sources. It's this system that will allow the robot to sense, process, and interact with its environment. The heart of this electronic network is the microcontroller, a small, powerful computer that will serve as the robot's brain. It will receive data from sensors, process it, and send instructions to the robot's motors. The assembly process also involves the integration of various components such as sensors, actuators, and power sources. Sensors enable the robot to perceive its environment. Actuators allow it to interact physically with the world, and of course, power sources provide the energy needed for the robot to operate. Each of these components plays a vital role. The sensors, for instance, might include cameras for vision, microphones for sound detection, and pressure sensors for touch. The actuators might be motors that allow the robot to move its limbs or wheels. Once the robot's body is assembled, it's time to bring it to life. This is achieved by connecting all the components together, ensuring that they're wired correctly to the microcontroller. After assembly, the robot is physically ready, but it still needs a brain. Now the stage is set for programming, where we will breathe intelligence into our mechanical marvel. But that's a story for our next scene. Stay tuned. A robot without a program is like a car without a driver. Without the right coding, our robot is nothing more than a collection of parts with potential. Programming is that magical step where we breathe life into our robot, allowing it to interact with the world around it. So, how do we program a robot? Well, it's all about breaking down complex tasks into simple, manageable instructions that the robot can understand. This is achieved through coding languages. Just as we use different languages to communicate with each other, robots understand instructions given in specific coding languages. Some of the most commonly used languages in robotics include Python, C++, and Java. Python, for instance, is popular due to its simplicity and readability, making it an excellent choice for beginners. C++, on the other hand, offers high performance and control over the hardware, making it suitable for complex robotic systems. Java, known for its write once, run anywhere capability, is used in large-scale robots where portability and network communication are key. Now, giving a robot the ability to perform tasks is one thing, but how do we make it aware of its surroundings? This is where sensors come into play. Sensors are the robot's eyes and ears, allowing it to perceive the world around it. These could be anything from cameras and microphones to more specialized sensors such as infrared or ultrasonic sensors. For example, a robot might use a camera to visually navigate its environment, or an ultrasonic sensor to detect objects in its path. By integrating these sensors and programming the robot to respond to the data they provide, we can enhance its functionality and adaptability. Remember, programming a robot is much like teaching a child. It's an iterative process of instruction, practice, and refinement. As we program, we learn more about our robot's capabilities and how to optimize them. With programming completed, the robot is almost ready to go, but not quite yet. There's still one more step, testing and refining, and that's what we're going to delve into next. So, stay tuned. The final stage in building a robot is testing and refining. This phase is all about making sure the robot performs as expected and making necessary modifications to get it right. It's like a dress rehearsal before the big show, and it's every bit as important as the design, assembly, and programming stages. Let's first talk about testing. Testing a robot is a meticulous process that involves examining every aspect of its functionality. It's not just about does it work or not, rather it's about does it work as intended? If the robot is designed to pick up objects, does it do so smoothly and efficiently? If it's programmed to navigate a room, does it avoid obstacles and find its way around? These are the kind of questions that guide the testing process. Then comes refining, which is the art of perfection. It's about making those small but significant adjustments that transform a good robot into a great one. Refining could involve tweaking the mechanical structure for more stability, adjusting the electronic components for better performance, or fine-tuning the software code for more precise control. It's a process of trial and error, of iteration and improvement that continues until the robot meets the desired standards. Sometimes, testing and refining can reveal a need for a major overhaul. Perhaps the robot's arm isn't strong enough to lift the intended weight, or its sensors aren't sensitive enough to detect subtle changes in the environment. In such cases, it's back to the drawing board, redesigning, reassembling, and reprogramming as needed. But that's all part and parcel of robotics. It's a field where failure is not a dead end, but a stepping stone to innovation. Through testing and refining, the robot is now ready to perform its tasks, marking the end of the building process. It's a moment of accomplishment, a testament to the power of technology and a promise of what's yet to come in the fascinating world of robotics. From a simple idea to a functioning machine, building a robot is a complex yet fascinating process. It all begins with a detailed design, a blueprint of sorts that outlines the purpose, structure, and components of the robot. This is the skeleton, the foundation upon which everything else is built. Next comes the assembly, the process of selecting the right materials and piecing together the mechanical and electronic parts, just like a jigsaw puzzle. Then we dive into programming, the heart of the robot. This is where we breathe life into our creation, using coding languages to dictate its behavior and integrating sensors for perception. But our work doesn't stop there. We test and refine, ironing out any kinks and making sure our robot functions exactly as we intended. Each step is a critical part of the journey, a dance of mechanical, electrical, and software engineering that brings our vision to life. Building a robot is indeed a journey of innovation and creativity that shapes our future.